In this video, I'll be going over how to locate absolute extrema. So if we're given a function f of x that's continuous over some closed interval, let's say from a to b, here are the steps we're going to go through. First, we want to find all the critical points for the function inside the interval a to b. And for this, we only really care about what's happening inside the interval. If we want to find the absolute extrema, we'll always be concerned with some specific intervals. That interval may be all real numbers, negative infinity to positive infinity. But to find the absolute extrema over some given interval, we just want to find the critical points in the interval. Next, we want to evaluate the critical points and the endpoints for f of x. Okay, so once we find the critical points over the interval, again, the critical points are just where the value of the derivative is equal to 0. We want to plug those into the function, and we also want to input the endpoints into the function, because the endpoints could also be where the function has its max or min values. So critical points and the endpoints into the function. And then once we input those values into the function, we want to see which of those output values are the greatest and the least. And those are what our absolute extrema are going to be. And recall that by the extreme value theorem, over a closed interval, there must be extreme. I have a hard time saying that sometimes. There must be absolute extrema. So over a closed interval, there must be absolute extrema. So we're guaranteed by the extreme value theorem to have an absolute maximum value and an absolute minimum value if the function is continuous and we have a closed interval. So let's look at a few examples of how to do this. Okay, so we want to find the absolute extrema for the function f of x is equal to 2x cubed plus 3x squared minus 12x plus 4, and the interval we're concerned about is negative 4 to positive 2. So first, is this function continuous over this interval? Well, we have a polynomial function. Polynomial functions are continuous for all real numbers, so that means that f of x is certainly continuous in this interval. So what we want to do is we want to find the critical points for the function. That just means when is the derivative of the function equal to 0. So let's take the derivative of f of x. It's going to be 6x squared plus 6x minus 12. And then we want to set that equal to 0 to find the critical points. So let's see, I'll factor out a 6. X squared plus x minus 2 is equal to 0. This factors to x plus 2, x minus 1. So the critical values we get are negative 2 and positive 1. So these are the critical points. I think I said values, but critical points here are x is equal to negative 2 and x is positive 1. Okay? So we found the critical points. So what I'm going to do is I'm going to just make a little table here. And what I want to do is I want to plug these critical points into the function, but we also want to plug in the endpoints of the interval. So we're going to input negative 4, negative 2, 1, and 2. So the two critical points and the two endpoints for the function. So substituting these in for x into the function, when I input negative 4, I get out negative 28. Negative 2 gives us positive 24. 1 gives us negative 3. And 2 gives 8. Okay, so where's the greatest value? I should say, what is the greatest value of the function? What is the smallest value of the function over this interval? So the greatest value is going to be positive 24. The smallest value is going to be negative 28. So what we'd say is the absolute max is 24, and that's when x is equal to negative 2. And then the absolute min is negative 28, and that occurs when x is equal to negative 4. So let's do another example, but this time, it's going to be the same function as what we just had, but this time the interval is going to be 0 to 2. So just like before, we wanted to find the critical points, and the critical points are going to be the exact same as what we just saw because the function is the same. So the critical points are going to be x is equal to negative 2 and positive 1. But we need to be careful here because negative 2 is not actually in the interval 0 to 2. So that means we don't need to consider negative 2 as either a max or a min value. So when we make the table, we can exclude negative 2 as an x value. So we're just going to use 0, 1, and 2. So when we input 0 into the function, we're going to get positive 4. When we input 1 into the function, we're going to get negative 3. When we input 2 into the function, we're going to get positive 8. So the max value here is going to be 8, and the minimum value here is going to be negative 3. So we'd say the absolute max is 8, and that occurs when x is equal to 2. And the absolute min value here is negative 3, and that occurs when x is equal to 1. So we need to be careful about what happened up here. We don't want to consider negative 2 as a critical point because it's not in the interval. If we did, when we input negative 2 into the function, we get a positive 24. So we would incorrectly have identified an absolute max value if we were to use negative 2. All right, we'll wrap the video up with this example. Suppose the amount of money in a bank account after t years is given by the function a of t is equal to 2,000 minus 10t raised to the 5 minus t squared over 8. Find the min and max values of the account during the first 10 years the account is open. Okay, so for the first 10 years, that means our interval that we are dealing with is from 0 to 10. And if we want to find the min and the max values of this account, another way of saying that is what's the absolute min, what's the absolute max over the interval 0 to 10 for this function. So in order to do this, we're going to find the derivative of a of t, so a prime of t, derivative of 2,000 is 0. So we need to find the derivative of this function. And I'm looking at my notes and I missed something in the function. So let me clean this up a little. We want to have 10 times t e raised to the 5 minus t squared over 8. So we need that e in there. Okay, so let's take the derivative. So we said the derivative of 2,000 is 0. Here we have a product. We have t times e raised to that exponent. So we're going to use the product rule here. So the derivative of the first function, as it were, we could say negative 10t. So the derivative of that is going to be negative 10 times e to the 5 minus t squared over 8 plus the derivative of the first function, negative 10t, times the derivative of the exponential function, so e 5 minus t squared over 8 times the derivative of that exponent. So the derivative of 5 minus t squared over 8, that's going to be negative 2t raised to the first power over 8. Simplifying this a little, we see that we have a 10e to that exponent in each term here. So I'm going to factor that out. We'll say 10e to the 5 minus t squared over 8. And then in parentheses, we're going to have negative 1 from the first term. And then in the second term, we'll have we have a t, let's see, we have a t right here, and then we have this t. So we're going to have t squared, and I can reduce this 2 and the 8 to 4 in the denominator. So what we're going to have is negative t times negative t, so that's positive t squared over 4. So kind of a little messy there, but if you're not following that, pause the video and see if you can get to what I'm getting at. So what we want to do is we want to set each of these factors equal to 0 and solve for t. So 10e to the 5 minus t squared over 8 is equal to 0. So when will this be equal to 0? Well, this equation will never be equal to 0. This is an exponential function. If you think about the graph, the exponential function is going to look something like that. That's the parent function, but we don't have any vertical shift down, so this will never cross the x-axis. Another way of thinking about this is, well, I can divide both sides by 10. So 0 divided by 10 will just still be 0. I can never get this expression equal to 0. If t is a positive number, I'm going to get a positive number for that expression. If t is a negative number, still get a positive value. And if t is 0, that'll just be e to the 5th. So this will never be equal to 0. So for this equation, we're going to say no solution here. So that equation does not yield any critical points. For the next equation, negative 1 plus t squared over 4 is equal to 0. So if I add 1 and then multiply both sides by 4, I'm going to get t squared is equal to 4. And then t is going to be plus or minus 2. So since t is representing a number of years, and our interval here is from 0 to 10, we don't care about negative 2. We're just going to use positive 2. So that's our critical value. And then we also need to consider the values on the endpoint of the interval, so 0 and 10. So what we're going to do is we're going to evaluate the function at 0 years, at 2 years, and at 10 years. And let's see what those values give us. So when we input 0 for t, we're going to get 2,000. When we input 2 for t, we get $199.66. When we input 10 for t, we're going to get $1,999.94. So what we see is that the max value is right here, and that occurs actually when the bank account is open. It's like we deposited $2,000 right off the bat. And then it looks like the value of the account dipped pretty severely at the 2-year point. And then after 10 years, we're almost back up to $2,000. So the max value is $2,000, and the minimum value is $199.66.